Hello friends, today we are going to see thermoelectricity. I am Dr. Gerald Anthony, Assistant Professor in Chemistry, St. Xavier's College, Palayangotte. So in thermoelectricity, there will be two points P and Q, two junctions which are maintained at a temperature of T and T plus dt, at two different temperature, a condenser and a potentiometer. These are all the general diagrammatic representation of the working instrument used in this thermoelectricity. So thermoelectricity consider of a thermocouple. Thermocouple A and B which are connected thermocouple P and Q are connected through a metal wire. A and B are kept in two heat reservoirs 1 and 2. So the junctions P and Q will be maintained at two different temperatures T and T plus dt. A condenser 3 is connected to this circuit. So since there is a temperature difference between P and Q, you please note down, draw the diagram which I have shown in the first slide, which will be helpful for you to understand it. So you can see in which there is the two junctions P and Q are maintained at a different temperature. Due to the temperature difference, an EMF is produced, which is measured under the zero current using a potentiometer. So here there will be no current, but due to the difference in temperature, an EMF is produced. So here you can see the temperature of reservoir 2 is T plus dt, and the temperature of the reservoir 1 is the reservoir 1 loses heat and reservoir 2 gains the heat. So the heat lost by the reservoir is represented as minus del Q and gained by the reservoir is plus del Q. So the production of EMF, since we are maintaining a different temperature, so due to the temperature difference, EMF is produced. It is called a Seebeck effect. So the potential, that is the potential which is produced due to difference in temperature, is known as thermoelectric power of the thermocouple. Thermocouple means two joints, two reservoirs which are maintained at different temperature. So the thermoelectric power E is given as change in potential with respect to temperature, change in temperature in which the current is kept as zero. Here, suppose assume that the two junctions P and Q are maintained at the same temperature, and if the electric current is passed through the circuit. So here in the second case, if the electric current is passed through the circuit, the junctions P and Q are kept in the same temperature. So what happens? Absorption of heat at one junction and the liberation of heat at the another junction will take place. So there in the first case you can see we have maintained the two junctions at a different temperature and potential is produced. Here you can see, here we are maintaining the temperature as a constant between the two junctions P and Q. Now electric current is passed through this circuit. Here at one junction there will be absorption of heat and another junction there will be the liberation of heat. This is known as Peltier effect. So the Peltier coefficient pi is known as the flow of heat per unit current. That is, the heat flow is taking place purely due to the flow of current. So the heat flow is represented as J, that is in the numerator, and the current flow is represented as I in the denominator. Here you can see the temperature is 0. Consider the entropy production. So the entropy is equal to change in heat with respect to temperature. S is equal to del Q by dQ by dt or dQ by T. So here you can see, you can find the entropy change in the two reservoirs 1 and 2 in the junction P and Q and the condenser 3. So here you can see in the condenser there will be a potential difference, electrical potential difference is noted in the condenser due to the flow of charge from either junction 1 to 2 or 2 to 1. So the from junction 1 to 2 or from 2 to 1 there may be a transfer of charge which leads to the electrical potential difference. So now the entropy change can be noted as TDS1, that is for the junction P or reservoir 1. It is minus del Q, that is here there is a loss of heat. Here you can see T plus D2S2. Here you can put del Q. So here the gain of heat. Here the entropy change at the condenser. So it is given as ds3. Here you can see there will be a change in electrical potential due to the flow of charge from one point to another point. So only it is given as minus dq d psi e. So now you can see the total entropy change in the working model will be ds, that is equal to ds1 plus ds2 plus ds3. So here you can see you can find the ds1 value. From here you can find the ds1 value and ds2 value and also ds3 value from the above three equation, and which can be substituted here. So here you can see we are going to substitute the values for, we have substituted the value for ds1, ds2 and ds3. Here you are taking the first two equations, you are taking the LCM for the first two equations. So you will be getting t square plus dt, and the numerator will be also changed into t minus t into dt, t plus dt plus t. In this way this minus t and this plus t get cancelled, and you will be getting minus dt in the numerator, and in the denominator you will be getting t square plus dt. So it is more or less equivalent to t square. So here we have converted it into t square in the denominator, and here you can see in the third part of the equation, that is the ds3 is remaining as such. Till now I have not done anything, any changes in the third part of the equation, that is ds3. So now you can see you can divide by dt throughout the equation. Now throughout the equation when you divide with dt, so here ds by dt, here del q by dt, here dq by dt. So the final equation will be as such, the third equation will be as such. So the equation 3. So now the rate of entropy production is the sum of the products of fluxes and forces. So you might have gone through my previous YouTube video about the Onsager reciprocal relationship, in which we have a detailed discussion about the fluxes and forces. Now the J1 is the rate of flow of heat, and J2 is the rate of flow of electric current. So J1 is equal to del Q by del dt, and J2, since it is a flow of the electric current flow will be due to the flow of charge, so it is represented as dq, which we have discussed in the previous slide. So the corresponding forces will be measured as follows. For the corresponding force for the flow of heat can be given as x1, and same way the corresponding forces for the flow of electric current can be given as x2. So we can derive the x1 value. We can select the x1 value from the previous slide, that is minus dt by t square, and the x2 will be minus d psi e by dt. So the phenomenological equation, as we have already discussed in the Onsager reciprocal relationship, J1 is equal to L11 x1 L12 x2. So J2 L21 x1 plus L22 x2. So we already know how to put this phenomenological equation for the different types of process, which we have discussed in the Onsager relationship. So here you can see L11 will be thermal conductivity, and L22 is the electrical conductivity. Due to charge flow, L11 thermal conductivity due to difference in temperature. So L12, So one will be one two will be heat induced electrical flow. One represents the heat and two represents the electrical flow. And here in same way, here you can see the two represents the electrical flow and one represents the thermal flow. So the thermal flow due to electrical conductivity or difference in potential. So the 2 1 is the thermal flow due to electrical flow. So the one always represents the heat and two always represents the electricity. 2 1 means the electrical flow is due in the sorry the thermal flow due to the electrical flow. So which we have already discussed in detail in the Onsager reciprocal relationship. So here you can see 1 2. So one represents the thermal heat or thermal conductivity. 2 represents the potential difference or electrical conductivity. So 1 2 means here the final number 2 represents the electrical flow, but the 1 represents the heat flow. So due to the heat there will be a flow of current, and 2 1 means here the 2 represents the electrical flow and the 1 represents the thermal flow, that is the different thermal conductivity. So the one, since the one is in the final one is in the prefix as it is given as 2 1, so the 2 represents the actual process, the final process which is going to take place. The final process will be represented in the prefix. And the here you can see the 2 1. So 1 2 means 1 means it will be representing the heat flow. Due to that heat flow, the resultant process is the electrical flow. Here 2 1, so 2 represents the electrical difference, electrical potential difference, and 1 represents the heat flow. Wow. So the heat flow, the final value 1 will be the actual resultant process, the 2 will be due to the potential difference, there will be a electrical flow. So always when you can see, if the first number represents the induced the cause of the particular process, and the second value represents the resultant of the particular process. So here you can see, now you can write the phenomenological equation. We can derive the we can get the x1 value and x2 value from the previous slides. So here we are substituting the x1 and x2 values, we are getting equation 4 and 5. So the phenomenological equation, here we got the phenomenological equation. The j1 j will be representing the heat flow, and j2 represents the electrical flow. Here you can see the L11 represents the heat flow due to difference in temperature. L12 represents the heat flow due to difference in the potential. In same way, L21 represents the electrical flow due to thermal difference in thermal conductivity. L22 represents the difference in the electrical flow due to the difference in the potential. Alright. So here you can see for Seebeck effect, which we have already discussed in the previous slide, Seebeck effect current flow will be 0. So J2 will be 0 and D2 will not equal to 0. Hence equation 5 becomes as follows. So the EMF measured will be also given as EMF E is equal to minus integration of d psi E by dx into dx. The dx can be cancelled. So by putting the dx in the numerator and denominator will not change this equation. So EMF is equal to change in potential. So that is given here. So actually EMF E is equal to change in potential. So here we are representing it as integration of d psi E. So the thermoelectric power, so to find the thermoelectric power, we know the formula is dE by dt. So as soon as when you put the d value here, dE by dt, so here you can see the integration can be removed since we are putting d here, so the integration is removed. So minus d psi e by dx into dx, we are having the e value as such here, that since we are putting dE, the integration, since the integration symbol can be removed since we are putting de in the left hand, d value, d in the differentiation symbol in the left hand side. So remaining values will be as such, we can write minus d psi e by dx can be written as such here, d psi e by dx into dx by dt. So that here you can see that dx can be now cancelled, so this de by dt is equal to minus d psi e by dt. This is, so here you can see this is equation 6 and this is equation 7, which we have derived in the previous slide itself. So comparing the equation 6 and 7, so here dE by dt is equal to d minus d psi e by dx into dx by dt, that is equal to minus d psi e by dt. So here is, you can see instead of this minus d psi e by dt, we can substitute this minus 1 by t L21 by L22. So this minus get cancelled, it will become plus 1 by t L21 by L22. So please note that this equation 6 and 7, we have already derived this equation 6 and 7 in the previous slide itself. So here we already know that J1 value and J2 value. So now, so here you can see in this J1 value and J2 value, which we have derived in the previous slides, for Peltier effect dt will be equal to 0. For Peltier effect there will be no change in temperature. So obviously in this equation 4 and 5, the dt minus dt by t square will become 0. In that condition, the first part of the equation L11 of J1 will become 0, and L21 of J2 will also become 0. In that occasion, here you can see you will be having only the values, the second part of the equation will be available, L12 and L22. Only this part of the equation will be available. So as soon as when you have substituted this dt is equal to 0 in the equation 4 and 5, here you can see both this part of the equation will be cancelled, so which I have marked with red color. Now, when you divide J1 by J2, you can see this dou psi E by dou t minus dou psi E by dou t get cancelled. You will be getting the resultant one value L12 by L22, which is given here. So the Peltier coefficient is pi. So the pi is equal to L12 by L22. So so here you can see the equation 8, dE by dt is equal to 1 by t L21 by L22, and the equation 9, the Peltier coefficient pi is equal to L12 by L22. Here you can see if you bring the L22 opposite side, it will go to the numerator, and the pi which we bring to opposite side of the equal to sign, it will go to the denominator side. So this becomes L22 is equal to L12 by pi. This is equation 9a. It is represented as 9a. So now here you can see. So when you are substituting the value of L22, that is equation 9a, into the equation 8, the equation 8 and all we have already derived in the previous slide. So when you substitute this value here, now this dE by dt will be equal to 1 by t into L21 by L12 by pi. So now from this equation we can write the value for L12 by L22. So here the denominator there is L12 and the numerator L21. When you rearrange it, so you will be getting the equation as such. L12 by L21 is equal to pi by T into dE by dt. This is equation number 10. So next, so for Seebeck effect, you can see the required condition is a temperature gradient, that is temperature difference, which gives rise to heat flow. So as a result, potential gradient is observed. So there is a difference in potential is observed in the thermocouple. So for Peltier effect, the required condition is a potential gradient, potential difference. So the potential difference leads to a current flow. As a result, now temperature gradient is observed in the thermocouple. Temperature difference is observed in the thermocouple. Thermocouple means the PQ junctions. Now it will be acting as a thermocouple when there is a difference in temperature. So in this sense, you can see the two phenomena, the Peltier effect and the Seebeck effect, both are coupled. So with this, we are completing this. Thank you.